In the last two video chunks, we first went through the big bird's eye picture of the EM algorithm and what it involved. And then we went through a very concrete example of applying it to a 1D mixture of Gaussians clustering model. And at the end, we said, although there's a little bit more technical detail involved, you can generalize that derivation to handle multivariate Gaussians in the general vector observed value case. So what we're going to do here is we're now going to go and look at an implementation of that EM algorithm, and we're going to apply it to a real data set. And the real data set we're going to look at has two-dimensional X, so big D equals to 2 using our notation here, and it's going to have what we thought before were 3 clusters in it. And the data set, if you remember, was the data set we looked at that broke the k-means clustering algorithm because it had this big fat cluster in the middle that wasn't very tall and these 2 roughly spherical ones either side. And although our intuition was it should be clustered in the way I've shown into these 3 different clusters, the k-means algorithm had this pathology where the top cluster grabbed all of those data points and the bottom cluster grabbed all of these data points. And the fact that the clusters had different shapes really screwed things up. So the hope is if we fit our mixture of Gaussians model to this, and a mixture of Gaussians model allows different clusters to have different shape covariances, that means that we hope that this middle cluster will learn to have very high variance in the X1 direction and low variance in the X2 direction, and therefore those points on the edges will get correctly clustered to be in that middle cluster. Good, so that's the hope. To apply the EM algorithm, what we need to do is the following. So in the E step, we talked about you just need to implement 3 lines. So the 3 lines we said were for each data point, you compute the joint probability that it came from cluster K and that the observed value would be the observed value that it was given the current setting of the parameters. You then compute the normalization constant for this, so UN by summing over K. You do this thing, and this, of course, is equal to just the probability of Xn given theta. And then you divide the 2 together, which gives the responsibilities. So you take UNK and divide it by UN, and that basically applies Bayes' rule to compute the responsibilities RNK. I will be showing the responsibilities on the plot on the left-hand side. And the way that I will show the responsibilities is if the responsibilities in this case, so let's look at Rn, so for the nth data point, we'll have Rn1, Rn2, and Rn3. The probability we come from cluster 1, cluster 2, and cluster 3, given the current settings of the parameters. If these things are really close to a third, i.e. we're not certain which cluster the data point has come to at all, then we will show things in gray. And to start with, where we've not performed any updates or anything like that, I'm going to initialize the responsibilities to be just that, 1/3, 1/3, 1/3, and that's why all the data points are shown in gray. From that point forward, as we iterate the EM algorithm, if you're more likely to be assigned to, say, the blue cluster, I will start to shade the points in blue. So you'll quickly see that these points at the top right here, which are a bit closer to the blue cluster, they'll start to be tinged by blue, indicating we kind of think that they come from the blue cluster. And they'll get more and more darkly colored as the algorithm progresses, indicating that we're getting more confident. Okay, so that was the E step, which implements the 3 lines as shown. The M step will now update the cluster centers, M, the mu's. I've used 2 slightly different symbols for this, mu and mk. They're both the same thing. They're the center of the Gaussians. And you should think of them as playing exactly the same role as the clusters centers in the k-means algorithm, essentially. So these 2 notations are kind of interchangeable. The M was what we used for k-means, and mu is what we sort of used in the slides for the mixture of Gaussians model. They're the means of the Gaussians. The second update will update the covariance matrices, and then the third one will update the pi-k's. Okay, so again, 3 lines needed to implement each one of those parameter updates. In addition to these E and M steps, you need to add a couple of other lines. Firstly, an initialization step to initialize the parameters of the model. So I have initialized the prior probability of coming from each of the clusters as a third, a third, a third. I've initialized the cluster centers or the mean parameters mu in the way shown by the blue, red, and magenta dots. So that's just showing the settings for the mu's. And the variances or the covariances, I've just indicated that I've initialized them to the identity matrix to start with. So isotropic variance 1 in each direction. And I've put little ellipses around each of the clusters to indicate what those covariances look like. So at the beginning, they'll be circular because they're initialized to identity, but they'll start to become ellipses in general, indicating the shape of the covariance matrix. Good. And there's one final thing that's often useful to implement or to add to your EM algorithm, and that is to compute the free energy. So the free energy is very easy to compute in the case of the mixture of Gaussians model, and it's useful to keep track of it just to check your implementation to make sure that it is indeed increasing or not decreasing as we run each E and M step. So this is a good way of catching bugs. You can also use it to define convergence as well by monitoring the free energy, and when it doesn't change by more than some tolerance value, you can then terminate the algorithm. Good. Okay, and we're going to plot the free energy not as a function of the number of iterations, which is perhaps what would be more usual and a perfectly fine thing to do, but we're actually going to plot it as a function of one of the parameters of the clusters, and that's going to be important for actually the next example in a minute. So I think in this example, I plotted it as a function of the component of this cluster here. The component of the mean of this cluster here. Good. Okay, so now let's run the algorithm and see what happens. So to begin with, we're going to start everything with an E step. And you can see at the end of an E step, the responsibilities for these data points up here are that it is more likely that they come from this blue cluster. And so they get tinged blue. And similarly, these ones down here are more likely they come from the magenta cluster, so they get tinged magenta. We're not absolutely confident at the minute, so they're not going brightly colored. And in fact, all of the data points in the middle, we still don't really have a clear idea. Do they come from magenta, red, or blue? Because all the clusters overlap there, and so there's a good chance that they came from any one of the clusters. So they maintain their original gray color. And we've computed the free energy down here and plotted it. Good. Okay, so that's the first step. Here's the second step, the M step. So we go and update the parameters here, and you can see sensible stuff is happening. The blue one has grabbed all of these data points, and so it starts to look like a elongated Gaussian distribution with a cluster center is at the center of mass of those points. Similar things happen for the other clusters. And again, our free energy has increased here, which is reassuring. And you can see that the mean of this cluster in the X1 direction is plotted here on the plot at the bottom. Good. And now you do another update of the responsibilities. And we're starting to see that the magenta cluster and the blue cluster are starting to settle on the points towards the left and right, respectively. And we do another M step, and we do another E step, and we keep iterating this thing forward. And you can see that interesting stuff starts to happen around now. So notice what's happening for this blue cluster. The blue cluster here has obviously grabbed all of these points, but because it's elongated in this direction, so its contours of probability for this cluster will be looking something like this. It's grabbed all of these points in here at the moment from this red cluster. I guess that makes intuitive sense. But the red cluster now not only grabs all these points in the middle with fairly high probability, it also grabbed these ones out here, and that's because its contours of probability are looking like this, and so these have higher density under the red cluster than they do the blue one, even though maybe this distance is a bit smaller. So learning these covariance matrices ends up giving sort of non-trivial trivial behavior. Okay, let's carry on running this thing forward, we can see that things are starting to converge a bit now. The blue one is starting to grab less and less of the red cluster, and soon everything starts to look hunky-dory, and we end up with perfect clustering essentially of the data here. And you can see that this mean here is starting to converge on a value roughly of 1.5, which is where the center of that cluster is actually set. And at this point it's converged because the free energy isn't changing anymore. We've hit our tolerance threshold, and we return this to the user. So we can see in this case, the k-means algorithm has been improved upon by this probabilistic variant. It's able to handle clusters of different shapes and sizes, which is a big improvement. And we also could return soft assignment of the data points, although in this case, now we've sorted out the shape of the clusters and allowed them to be different, we're actually pretty confident about which data point every cluster came to.